Like you're gonna waste your time.
I'm gonna do it again for summer, so I don't know if I do it again for summer.
It's an easy process. 40 hours.
All right, so
This will be this.
guys, that number 3. I'm sorry. 4C. I think I told you this yesterday. You have to understand. There are concepts we are learning, and there are a lot of different ways to come at them. And not every single problem I talk about or give you will be generalizable, right? It's just a quirky little thing, little side note, little interesting thing. If you kind of understand where it's coming from, that means you understand the idea better. Am I going to give you a problem like that on the actual mini test? No. Why would I do that? Right? So it was an interesting thing to have on there to make you think about, to talk about, and then move on. Right? So no, that's not going to be on there. Okay? Anything else from the probability stuff before we get into new stuff? Anything left over from probability? Yes?
Can we do 1C?
Oh, where did I put them? What's 1C say?
Probability that at least one.
Oh, okay. So,
I just understood something. Sorry.
oh, shit. Go, oh, like that. Don't go, you know.
Eureka.
Sorry.
I was like, is she having a heart attack?
That's some like ceiling caving in or something.
Be like a Archimedes. Eureka, and just run across the street. Somebody's gonna die today. Oh no.
What's the probability of A plus the... I'm answering the question. I am. What's the probability of A plus the probability of not A?
1 minus 8.
No, come on. It's the probability of A plus the probability of not A. It's 1.
One.
Oh yeah, 1.
Because what does it leave out? Does that leave anything out? Does this leave anything out? It leaves out B. Well, B is either A or it's not A. Right? Whatever the hell A is. What's A? Left-handed people. So what's not A? Not left-handed people. Right? See how I cover them? I don't say right-handed people because somebody's like, what if they don't have any hands? Oh, screw. Left-handed, not left-handed. Right? Unfortunately, sure.
Dang.
People could have no hands. That could happen. So cover my ass, left-handed, not left-handed. That covers.
It acts like B, right? It says that.
No. What's probability of A plus probability of B? I have no freaking clue. What's probability of A plus the probability of its opposite is 1. So therefore, what's the probability of A? It's 1 minus the probability of the opposite of A. Now, if this is the question, and it involves 18 things I have to calculate, but the opposite situation involves one thing I have to calculate, shit, yeah, I'm going to do this. But in order to answer my question, I better do 1 minus what I get. So, you look at 1C. Probably at least one, what's it say? Likes it?
Yeah.
Now, this is not why it works, but this is why I do what I do on this problem. The probably at least one likes it. So how many ways is there for at least one to like it? The first one could like it, and the other two don't. The middle one could like it. The last one could like it. Or two. At least one is two. Maybe the first two like it, and the last one. Or maybe the middle two that like. Or maybe the first one. Or maybe all three of them. So I'd have to calculate the probabilities of all of those and then add them up. Now that'll work. That would work all day long. But what's the only thing I leave out? What's the opposite of at least one person likes it?
None of them.
Nobody likes it. The only thing I left out here is DDD, which is 1B. Look at 1B. So this would be 1 minus the probability that no one likes it, or all dislike it. So this is the idea that the probability of something is 1 minus the probability of the opposite of that thing. if the opposite of the thing has less work that I have to do, yes, I will do that. If you don't want to do the 1 minus shit, then you do all these, add them all up, and eventually you get to the same place the rest of us got, right? I like it. Me. So at least one is one of the most common uses of this idea. If I have 80 people and I want the probability at least one of them does something, I'd have to do the probability of 1, plus the probability of 2, plus the probability of 3, all the way to frickin' 80. Or I could just do 1 minus the probability of none of them and be done with it. And again, I put this up on the board yesterday. I think at least 1 would mean 1 plus probably 2 plus probably 3, right? So what's the only thing this leaves out? The probability of 0. And if I add all of these together, I'm supposed to get 1. So of course, 1 minus the probability of none equals the question I'm being asked. I mean, that's because all together they make 1. So the probability of one chunk is 1 minus the probability of the other chunk. Because together they make frickin' 1. Like that. Please let me make sense.
So 1 as in like 100%.
Yes, 1 as a decimal is the same thing as 100% as a percentage. Humans made percentages up. They're made up. I don't know if you guys understand that idea. Percentages are purely made up. Now, does that mean they don't have any application? No. That means that if I have 17% of 80, I don't do 17 times 80. 17% is made up. What numbers does that represent? 0.17. That's the number. This is the made up shit. Not completely made up, because what does percent mean? Out of 100. In fact, the percent symbol is 100. Right? Just kind of take the number 100, swoosh it around, you get the percent symbol. It's crazy.
Oh.
And that is 0.1 freaking 7, right? Okay. So yes, sorry, long answer, made short. Yes. How's that? Is that anything else left over from the probability stuff? No. Okay. All right. I love it. I gotta wonder sometimes. He thinks it's all right. Let me ask my question. I already talked about 4C. I'm not going to talk about 1. All right. Did I already talk about 4C?
Yeah.
So you could ask me, why did you do probability of A or B? Okay. The idea is any probability I calculate from any situation. What's the highest it could be? 1 or 100%. Right? That's the highest it could be. So on this problem I could go, all right, so every probability I calculate has to be at most 1. Let me look at the probability of A or B. Why? Because it includes the probability of A and B. That's a really good reason why I would look at it. So the probability of A or B would be probability of A plus probability of B minus the thing I don't know yet. 0.8 plus 0.4 is 1.2. That's illegal by itself, isn't it? Isn't 1.2 an illegal probability?
Yes.
Please say yes. 1.2 would mean 120% chance of rain. Again, my thing I said yesterday was giant rain, drops as big as 8 people. It's red, the umbrellas, it just laughs at umbrellas. Boom! Die. Right. Yes?
So, in general, math always works out. So, with
Math always works
is there
out.
any cases where you end up, someone calculates, like with math to be higher than that, you just cut it off at 100% saying that's the most it can be? Or does the math
If it's a probability
it always works?
and you get more than 100%, your calculations are incorrect somewhere. You could argue at some fringes of trying to interpret meanings or something more than 100%, but those are looking at things differently. I mean, you gotta. So yes, it's not us chopping it off at 100%. It's if the calculation is done correctly, that can't come out to be more than 100%.
Just out of curiosity on the like looking at stuff more like physics on like minuscule levels and stuff, like with electrons, all kinds of stuff. Do you get weird things that does that happen, or does it always work?
No, it can't. unless you alter your definition of probability, which, you know, that's what it would take. We're not going to talk about that here. Yeah. Probability, the way it's defined, it's got to be at most 100%, because beyond that wouldn't have any physical interpretation. So there are. I'm not going to say any more of that. But to finish up, so if the probability of A or B is 1.2 minus the probability of A and B, well, how big does the probability of A and B have to be to get it to be legal again? What gets it down to 1 again? At least 0.2. So it has to be at least 20% to get that back down to 1. What does it end up being? 0.34. Okay, that's at least 0.2. That makes sense. Okay. So a problem like 4C will not show up on anything except for this, because it's not graded and it's a discussion point, right? You guys have got to get beyond everything coming out of my mouth and out of the book is immediately applicable to what you're going to be tested on. No, these are ideas we have to explore from several directions, right? I'm going to test you on the basic use of those ideas. We're going to explore them in all different kinds of ways. Okay, I like it. Cool. Anything else from probability before we move on? Okay, all right. What I'm going to do today is I'm going to explain an idea behind what we do in Chapter 4. Okay, so there's going to be a lot of math I do today that's just exploring why we do what we do. So are you going to have to do some of the stuff I'm about to do on your own? No. Will it help if you follow along and it makes sense? Yes. Okay. All right, I like it. All right. And this is related to, have you guys ever taken a class that's not like mine, that like the test one is worth 200 points and the midterm is worth 300 points? All right, those people don't know math. If they're a math teacher, I'm a little concerned about them, to be honest, because they don't know how to work with percentages. That's why they put points, right? So if you have a math person doing that shit, I'm a little worried about that math person, right? So that way actually is a lot more straightforward to calculate your average, because you can see how many total points you got so far possible and how many points have you earned. Are you with me? But how do you do it in like an actual normal class where there's percentages of stuff? How do you calculate your average? Or that's going to be related to what we're going to do today. Okay, so again, I'm going to start from what we know, and I'm going to bring it up to what Chapter 4 is about. So let's say I have, for example, I have this data. Get out. Let's do this. 1, 1, 1, 1, 2, 2, 2, 3. What do I have? 4, 7, 8, 9, 10. I like it. All right. That's a nice set of data, right? If I ask you to calculate all the stuff that's going to be easy to attack it, are you with me? We're going to kind of attack it, but then we're going to create a new way of looking at things. What's the immediate thing about this data that stands out? A lot of repeats. I love it. So this is really all about, what if you have a bunch of repeats? Is there a better way to do the mathematics? Because what if I had 50 ones and 87 twos and 96 threes and 87 fours? I don't want to do it the Chapter 2 way. I don't. I'm like, is there a better way? Because there's a lot of frickin' repeats. The math should be able to do that quicker. Thank God there is. So let's attack this like we normally would, and then I'm going to transmogrify it into what we're going to do in Chapter 4. So what's a smart way to kind of do the average, for example? Let's say this is a population. Since there's repeats, I could say there's 4 ones plus 3 twos plus 1 3 plus 2 fours, right? And then divided by 10. Is everybody cool with that? I mean, there's repeats. I'm adding them up, which multiplication is repeated addition, so I can kind of use that to my advantage. Now on the side here, here's where we would go in Chapter 2. We would just go ahead and do this. What do you get? And 21, 2.1? Yeah, you get 21 over 10 2.1. So whatever weird shit I'm about to do, and it's not completely weird because it's trying to make the math here easier. If I have a huge list of data with a lot of repeats, I want a quicker way to do that shit. Right? But that's the old way of doing it. Here's the new kind of way, and here's the math behind the new way. Okay, so I really want people to understand that. I always have somebody go, did you already get the answer? What's this other shit? Oh, God. All right, we got the answer the old way. Let's look at a new way. Isn't this the same thing as 4 tenths times 1 plus 3 tenths times 2 plus 1 tenth times 3 plus 2 tenths times 4? Right? Isn't that the same thing as 0.4 times 1, 0.3 times 2, 0.1 times 3, plus 0.2 times 4? Somebody interpret this 0.4 for me.
Weighted average.
40%. 4 to 10.
40% of my data is ones. You with me? Now, of course, if you do this, it's still the same stupid numbers. I'm still going to get 2.1, am I not? I have to. But what is a way of capturing this? This table. Now, here is what Chapter 4 is going to look like. Or part of Chapter 4, anyway. First part of Chapter 4. Now, 40% of the data is ones. If I randomly selected a number, what's the probability I would get a 1? 40%, right? So the probability of X, also known as the weights. This is the weights of each one. So 1 is the heaviest weighted thing at 0.4. 2 is 0.3. 3 is 0.1. And 4 is 0.2. Does everybody agree with me that that is another way to represent this? How many ones do I have? 40% of my data is ones. This table could represent more than this, yes. If I had 100 numbers, this table would mean that 40 of them are ones. So forth, right? That's all it says is 40% of my data is 1, is the number 1. 30% is the number 2. So forth. Are you with me? So this is a little more generally useful then. Okay. So if I give you a table like this, could you make a list out of it? Yes. Are you going to have to? No, that's bullshit. If it's given to me like this, I'm going to do it this shortcut method we're going to talk about right now. Now, what is all these? What are each of these? What am I doing? Multiplying X times P of X. The weight times the number. 40% of the mean should be made of the ones. 30% should be made of the twos. 10% of the threes. 20% of the four. If I add all those together, I get the average. This is how you use weights. So if your test grade average was 70, I think it's like 50%, you would do that same. You would put your grade and the percent from the syllabus. Multiply, add, average. It's the same way, because those are weights. The percentages are weights of each of those data points. Tai Chi. So here I get, if I multiply across, if I do this, I did 0.4, 0.6, 0.3, 0.8. What do I get when I add all those together? 2.1. What symbol do I use for what I just did?
Summation.
The E, dude? I like it. So if this was like the number of TVs that several people owned, right? 40% owned one TV, 30% owned two, so forth. You with me? And I picked several people several times in a row, I would expect to get 2.1 average. Is that cool? If I pick several of these people at random, I would expect a 2.1 average TVs. Is that cool? This is the average, which is also called the expected value. Now, why is that so cool? Does it make sense I call the average the expected value? If the average age in here is 24, and I take a group of people, what do I expect their average age to be? 20 freaking 4. And look at the first 3 letters. Expected value. I mean, so if I say find the expected value, I'm going to use this formula. Now, the expected value means the average no matter what. If I have xp of x, the expected value is the sum of xp of x. EXP, freaking expected value. Okay. I'm sorry. Somebody have a question? Yeah.
Oh, the expected value is only referencing the population mean, right?
Yes. I like it. Yes.
Would you give us a list and want to have us do that?
Yeah, I'd have to give you the x's and I'd have to give you the p of x's. I wouldn't give you the list though. Again, this is the math. This is the idea mathematically of why this works. So what are you going to see? You're going to see x and p of x. And they're going to say find the mean when you multiply and add. Maybe. Now, the mean by itself we know by now is not good enough. What else do I have to be able to find?
Median.
That's still a measure of center. Mean won that test. I also need a measure of spread. Standard deviation. So the mean and the standard deviation is normally the best way to summarize any group of data. So every time we have another way of giving somebody data or having somebody give us data, I want to see, is there a quicker way to get those two numbers with that other way of giving me data? So here's another way somebody can give me data. So we developed a quicker way to get the mean. Now we got to develop another way to get the standard deviation. All right, so let's do that. Here we go. Actually, let me do this. Let's do it with a different set of data. You guys take a second and figure out the expected value for this. Let's see. Oh boy, all right. How do you check to make sure this is what's called a valid probability distribution? What do you think you would do? Yeah, they have to add up to 1, so hopefully I did that right in my head. You never know. You definitely want to double check me there. 70.
Tables and stuff.
Looks like it, yeah.
I often see that you'll have like 0, 1, 3, 5, and 11. If you're doing like a frequency distribution like that, when you're actually graphing, you have to leave that empty space. On the table, do you not have to do that? It's like if there's nothing in like the
Yeah,
20.
this is a calculation table. This is not a display. This is not used for anything other than calculating mean standard deviation, for example, right?
Well,
If I was displaying data to somebody like we were in chapter 2, then I'd have to be honest about there's missing stuff.
But like, in like a frequency distribution like chart thing going on, you still have to leave that blank space, or can you skip the one there's nothing in? Because you're not graphing it yet. You're just kind of trying to organize what you're looking at. Or is it better to leave that empty space there?
Well, the only reason we have like a class when there's really nothing in it is just so we don't forget it, or just so it doesn't look like we forgot it or something. You know what I mean? Here we're just saying there is no 2's, right? For some reason, there is no 2. Okay. So the sum of p of x is 1. There's another thing here we have to check that we'll talk about here in a minute. It seems almost too stupid to even talk about what we'll talk about. So I want you guys to figure out the mean. Are you guys doing that? Do you notice how L1, L2, L1 times L2, you could do these in the lists in the calculator if I give you a lot of shit here, right? Okay. This is not that much. So I want to do x times p of x. So here I get 0, 0.29, 63. What is it, 80? And I don't know, 1.09.
2.09.
2.09? Oh, you're so far off, Jeff. Screw it. Two, 3.81?
Yeah.
So the sum of x, p of x. You're really smart You get in the practice of telling yourself what the shit you just did. Don't just put 3.81. Tell yourself what you just did. So what is 3.81?
The sum.
Expected value.
It's the average. I love you guys. Right? 3.81 is the expected value, or better known as the mean of this data. Right? Why did the 11 not affect it as much? It's a much bigger number, but where's most of the data? 1. So most of the data is around here. This did pull it up to 3.81, but most of the data is right here. Do you guys see that? Now, if you just take these 5 things and average them, what do you get? What's the average of these?
16, 20.
4,
divided by
right?
4, yeah.
This adds to 20 divided by 5 is 4. You get an average of 4. But why does that not make any sense here? You would only do that if they were all equally weighted. But here, 1 is more important than 3 is more important than 11. You know, maybe. All right. Do you actually have to know that to do any of this work? No, but it's kind of nice to know the heaviest weighted thing is where it's attracting. It's like the sun keeping the earth going around it. It's attracting it to it. I like it. Yes?
You say the average for elements 100.
Add them up, divide by 5. Yep. All right. All right, so now let's talk about standard deviation coming off of this. Somebody remind me, what's the formula for standard deviation? Remember, we're dealing with a population here, right?
X minus mu over n. Or
Square root of 1 over n. Oh, wait, I do it differently.
X minus mu divided by n. Squares.
Square over n.
I like it. In fact, let's just talk about the variance right now. Let's make this easier to look at. All right. So now, and remind me, what's the formula for the mean from before? Now watch. Now look, here's the formula now for the mean. What's the main thing that's kind of missing? N. But what's in the bottom of a probability? What's in the bottom of the probability? How do you make a probability? How many you're looking for divided by
The number.
how many there are. N. That's the same formula. Because what's in the bottom of the P's? N. So it's in there. It's like ragu. It's probably too old of a reference. All right. So what the hell's my point? I don't know. I forgot. All right. Everything's got to be weighted according to this. So I could make a column. I'm not going to because we're going to talk about a better formula than the one that would be officially used here. We're going to make it better. I could make a column of x minus mu and then square them and then multiply by the weight. Right, so don't write this. So I could do x minus mu, blah, blah, x minus mu squared, blah, blah, multiply each one of those by the weight, because each one occurs this many times. Each one occurs this percentage of the time, right? Same idea with the mean. My God, I don't want to make that many freaking columns. Right? None of us want to do that. So let's oh shit, let's use some algebra. I was told there'd be very little algebra. Well, here's where one of it happens. Let's use some algebra to help us make a better formula. But algebra's not useful, Jeff. Oh well. It's not true. All right. Now we're only going to do the first couple steps because you could have an entire semester's worth of a class about summation notation algebra. We're not going to do that. I just want you to buy into where it ends up. If you were in algebra class, what would be your instinct to do? What would be your instinct to do to that? I like that. But pure algebra, not graphing. Algebraic manipulation.
Substitution.
Foil it. There it is. To be honest, I don't like FOIL. FOIL is bullshit. I know some of you guys are like, I'm glad I didn't have any algebra sheet. But what's FOIL again? FOIL just means
Outside. First outside the line.
first outer. But that's bullshit. X gets a turn to distribute. -5 gets a turn to distribute. I don't need extra FOIL bullshit. If I put another term in here, does FOIL still work? No. It'd have to be something. There's a whole other term. Instead, or just think, distribute this guy, and then this guy gets a turn. All right, sorry. That's my little rant about FOIL. Beep. So how do I FOIL this, though?
X minus mu times x minus mu.
Yes. Something squared is it times itself. And what do you get?
Two x mu plus mu squared.
Squared minus 2 mu plus mu squared.
2 mu x, yeah. So you get the sum of this times p of x, right? Everybody with me still? A little bit? All right, I like it. Or at least look in this direction. Now, if I distribute this p shit, right? I get sum of x squared times p of x minus extra crap behind it, right? Is everybody cool with that piece? Just distribute the p of x through, right? Isn't it this whole thing times p of x? So I can distribute the p of x through. Now, the really weird thing is all these other terms, if you work with them, end up becoming, I'm going to write this again up here, end up becoming mu squared. So here is the formula we're going to use. For the mean, it's this. We already know this. We already did this. Bam. For the variance, it's this. Why is this a better formula, Jeff? That looks like shit, Jeff. You suck, Jeff. I'm out of here, Jeff. Thankfully, nobody's leaving. Well, look what I already have. Don't I already have x p of x?
Yep.
And don't I already have mu? Right? Don't I already have the mean? So I just need one more column. I need x squared p of x. That does not mean you square this. Why would that not be what you want? If I square this column, I get x squared p squared. I love it. That's not what the formula wants. So the way I do this is I just multiply these together. What is x times x p of x? X frickin' squared p of x. So this formula is better. It only requires one more column. It's what I call a calculation formula, whereas this is a conceptual formula. There's the concept. You still see the distance between the mean and the data points. That's the heart of a standard deviation. I lost that now, but this is the computation formula. This is the one that's easier to actually use. All right, I'll let you guys. So this formula here, forget about it. That's the idea. That's the official formula, but that's equal to this. This is not a different formula. This is the same as that one, just worked a bit. All right, Jeff, now show me how this freaking works, please, dear God, Jeff. Okay. We don't need all this other shit, thank God. I just need that one more column now. And don't worry, you know me by now, hopefully. Do have a handout. One side is a worked out example of this. The other side is the one you're going to do together in a minute. So I just need one more column now. So I do this. 0 times 0, 0. 1 times 0.29, 0.29. 3 times 0.63, 1.89. 5 times 0.8. 11 times 2.09. I don't know. What is it?
22.99.
22.99?
22.99.
22, yeah, Jeff. You can say it but not write it. Does everybody see where that came from? X times x p of x is x squared p of x. So I do this list times this list to get that one. Now if I add them, I don't get the variance. I get this piece of the formula, right? I got to plug it in. Same way we're used to that. I add them, I get a piece of the formula, I plug it in, I work it out. So I add these up, what do I get?
29.17.
Who is it? 29.17.
17.
So now if I plug that in, this is 29.17 minus the mean squared. The most common mistake is people forget to square that poor little dude. Yes, sir.
Could
their column ever be negative?
This year?
Yeah.
Yes. Why? How would that happen? Your variable could have negative values. Of course, it could be temperature in Alaska, right? Could be profit made by a business that's had a few rough years. Negatives, negative, negative. Yes. But then this one, can it be negative?
No.
Hell no. Probabilities are always above 0, below 1. And the x squared, of course. We don't have any imaginary values, thank God. So now, what's the variance going to be? What do you guys get here? Help me out.
14.6539.
14
How
point
did you get that?
blah, 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 blah. So then take the square root of that.
3.828.
Who's it?
3.828.
Oh, that's freaky, man. Why is that freaky? Why does Jeff think it's freaky? Because it's almost equal to the mean. That's neat. I wish I could say I did that on purpose. Is that what you guys got? 3.828? Has anybody else done that? Or are y'all just waiting for him to get finished?
But isn't 3.81 squared 10?
Yeah, it should be roughly 10.
So 2.9.
Or actually, it should, between 10 and 16. 3.81 squared should be like,
10.1124.
no.
Oh my gosh, I did 1.8. I'm so
Yeah, you must have done one. That's closer to 4. It should be closer to 16.
That's right.
This is right? Okay.
Yeah.
Thank you. Verification. It's not that I don't trust you. It's just good to have repeatability. What's up? Everybody all right?
There we go. 3.81.
Concerned faces out there. Yes, ma'am. So I did this. Actually, they did this. And whatever you get, you take the square root of it to get the standard deviation. Now again, does anyone know why I keep using population symbols here? What's on the bottom of the sample standard deviation?
N minus 1.
N minus 1. And here, P of X. What's on the bottom of P of X? N. So that's why it's got to be population.
So it can't be sample.
Can't be sample.
Can you do all this with the sample too?
Say again?
If you have the sample with the weighted, like the weighted mean of the sample instead of population?
There are ways you can adjust it, yes. Will we get into that? No. A lot of the adjustments you make would be in like a Stats 2 class if we had a Stats 2 class. A lot of the extra adjustments you would make. Okay. You guys, you want to take another break or you want to get into the handout?
No.
If we get into the handout now, we can leave earlier.
All right, handout.
Ah, see? So,
My brain hurts.
one side is a completely worked out problem. It goes a little bit further than what we did on the board. Should be used to that. And the back side has the exact same questions about a different set of data that I want you guys to work on. Okay.
Third row, fourth column.
So you did 3 times 3
Good.
So I put at the very top of the column what you would type into the lists in your calculator if you want to do it that way. You don't have to.